Hello everyone, this is Dilleswara Rao. Um, as you know, I'm dealing with automatic control of aircraft series of lecture. So on that, on the last class, we have discussed on stability augmentation system. So on the stability augmentation system, how that control systems have been designed for making it the frequency response should frequency response of aircraft should be minimized, and the control surface output signal will be stable in condition, and bring back that aircraft unstable conditions to stable condition, and how these SAS systems have been installed in aircraft dynamic systems to make it stable condition. Also, we have discussed on last class. So in the last class, we have discussed on pitch. Pitch augmentation system. So now we will discuss on lateral and directional augmentation system. So let's go into the topic. So this is called lateral and directional stability augmentation system. So as I said, stability augmentation system means what? When we are giving an input signal to a control surface, due to that input signal, that control surface will be operated. So like suppose you say we are giving a control input to an elevator input. So due to that elevator input, the elevator will be operated. So due to that, due to that elevator operation, the aircraft may pitch up or pitch down. So due to, when it is getting from cruise conditions to pitch up condition, so suddenly one one displacement will happen on aircraft, like that pitching moment will happen. So due to that pitching moment, the aircraft will be going to the unstable condition. So again, it should be it should be bring back to a stable condition. So for that, what we need to do, that elevator should be coming to its neutral position. When it coming to its neutral position, whole aircraft also should come to the stable condition. So then only aircraft will be easily will fly on will fly. So that means the total control over the aircraft will be having on pilot only. So in this way, this system, like this stability augmentation system, will help that pilot to. It's like an autopilot system only. It is an integrated system that will help that aircraft bring back to its stable condition. Like whenever it is going to that unstable condition, this SAS system will make that system to bring back to that stable condition. So for that only we are integrated this one. So previously we have discussed on that pitch stability augmentation. Now this yawing and rolling, like a lateral and directional augmentation system. So in this, if it is a lateral, means like turning or maybe like rolling. So that time, how that augmentation system will be helped to make it in stable condition. So on that way, so here you see that figure, it is showing now, like this is a figure, a block diagram of a lateral and directional SAS system. So here the basic augmentation system for lateral and directional system, that the body axis roll rate is feedback to that ailerons, or to modify the subsidence model, and yaw rate is feedback to that rudder to modify the Dutch roll mode. Like the Dutch roll mode means what? Like this one, and the spiral will be like this one. So when we are giving the feedback system, like feedback system is going to that bring back to that summing amplifier. So that feedback system here, how it is, where that feedback we are taking it is from the ailerons, that roll subsidence feedback we will take it out, and from the rudder, that Dutch that yawing feedback system. I mean, yawing feedback will be taking over. So that that lateral, like if it is a rolling motion, is not in general, like decoupled from yawing and side slipping motion, slide slipping like directional motion. So therefore, that augmentation system will be analyzed with aid of a multivariable state equation, like two inputs like ailerons and rudder, and two more outputs like two aileron outputs and one rudder output, like that. So that will be implemented from this figure. Like you see that a aircraft model integrator is there, no? From that two integrator, two inputs have been given to this one. This is a summing amplifier. So from this summing amplifier, that two input is given to that transfer function. Here you see that integrated transfer function. From the transfer function to that dynamics model, that signal will be gone out. So due to this signal, that aileron in output or rudder output will be like if you make it like this. So this will be like aileron output if it is a rudder output. So suppose for suppose if you say, so these two inputs will be I mean these two outputs will be giving to that control surface. So when this output signal is given as the input signal to that control surface, so that the control surface will be operated. So here for the separate transfer function is there, no, that GA and GR. So that GA is for aileron transfer function, and GR is for rudder transfer function. So here that transfer function is a thing that will gives you the output signal which will be incontrollable in pilot's control only, and they will have a separate feedbacks also here. You see that GF, GB, and KP. So that pitch rate and rudder feedback system, and here also that I mean this is for aileron feedback, and this is for rudder feedback. So for the rudder feedback also, in between there will be on another transport function is also included here. So this is another transfer function is GW. So and that rudder rate also, that roll rate also we have given as a feedback to, I mean rudder feedback to this summing amplifier, so that by taking the feedback from here, that signal will be compensated, and whatever the required input is there for this transfer function, that will be automatically adjusted, and that will be given to this transfer function. Okay. So see here, the purpose of this stability augmentation in IARE feedback is to use the rudder to generate yawing movement to opposes the yaw rate that will builds up from Dutch roll mode. Like when we are giving that feedback, yaw rate feedback to that one, so that feedback itself will generate the input signal in controllable way only. So that resulting feedback configuration is like a type 0, like a type 0 IARE command system with 0 command input. So this raises a difficulty that the coordinated like a steady state turn, the IARE has a constant non-zero value. Like I mean, if it is a type 0 command system, so due to this type 0 command system, this rises like a due to that without input, that I mean without input, that output is been following up. So this is like a type 0 type only. So it may be thought that the pilot could easily coordinate to turn by applying the correct unit command through that rudder pedals. So the flight control experience shows that this is not the case. Like when the pilot can easily coordinate, like if he is applying that yaw rate due to that rudder pedals, like rudder pedal is applying like that. So he cannot control the test period. I mean, he cannot control that much easily. So that yaw rate feedback will oppose the turn unless the pilot applies the necessary yaw rate command, and that the increased command needed to overcome the finite error of type 0 open loop, and it will be like an acceptable only. Like when you are forcefully applying that pedal also, that aircraft cannot be turned automatically. So there will be a limit to that yaw rate also. That limit will be overcome that whatever the default values are there in that integrator. So when it is overcome that default values, then only that yawing will be taking place, because these are all the directional control will not be that much easy. Like it is not like a bus steering or vehicle steering. Just you apply the steering so that it will be turning totally. That's not the case. So here, when you are applying that radar, also it won't be. I mean, it will check that input, whether this input is conventional, and if it is required to turn or not. That also it will be. I mean, first it will check, so that your input will be given to that transfer function. So here that input is been totally depend upon that feedback, your rate feedback only. So when that your rate feedback is sufficient, so that your rate will be, I mean, that yawing input will be given to that control surface, then that control surface will be operated. So even that the steepy back turn, like a bass, that when a steep turn is required, so the little rudder deflection is needed to produce that required yaw rate. So in high performance aircraft, the turn is essentially produced by rolling to the required bank angle and applying back pressure to that control sticks to produce the acceleration. Like whenever for a high performance, like a higher aircraft, like a passenger aircraft with heavy loads. So for that, there is not that much need of radar to make it that. I mean, whenever if it is a steepy, I mean, if it's a very steep turning, then only that radar is being applied. Otherwise, just that slide slip angle only. Due to that slide slip of banking only, the aircraft may take turn. So at that time, while taking the turn, also that back pressure control stick is being operated, so that that enough acceleration will be, because while taking the turning also, that back pressure, I mean, the back acceleration also required. Due to that acceleration only, it will take the turn easily. So that the simple solution for this problem to implement the add damper, yawing damper, is to wash out that circuit on that output of your rate sensor. So high pass filtering action of the wash out circuit remove the steady state component of your rate during the turns. Like I mean, whenever we are giving that your rate also, but it is not taking that completely. So for that, what we need to do, we need a washout circuit for that yawing input. So if you use that washout circuit, then it will take that yaw rate completely, so that the turning rate will be easily it can attack. So the output of that washout approximates differentiate. It has been differentiated the yaw rate. So this is like a still suitable for feedback for damping of natural mode. So in the previous figure, if you see that the GW is the washout circuit. So here you see this GW is there now. So this is called washout circuit. Washout circuit. So this washout circuit, and the transfer function for respective transfer function is GA. That represents the equivalent transfer function for differential acceleration for left to right, left and the right ailerons, and GR is the rudder actuator, and the transfer function GF represents the noise filtering and any effective lag at the output of roll rate and yaw rate gyros, and GB is the bending mode filter. So see here that GB is the bending filter transfer function. So like GA is the ailerons transfer function, and as we said, this is the rudder transfer function. Transfer function, and this GF is what GF represents the noise filtering and effective lag control output of I mean lag control output for roll rate and yaw rate gyros transfer function. So that bending mode filter is needed because of that movements generated by ailerons are transmitted through that flexible beam structure of the wing. So and that effect is censored by roll rate gyro in the fuselage. Like whenever we are giving that banking angle for that one, so due to that aileron deflection, that aircraft will be banked like that. Like you see, if it is like that, so it will be that banking will be like that. So this is the slide slip. So due to this banking, so there will be a bending effect will happen on that aircraft. Wing. You see this wing beam is there, no? So in this beam there will be a bending will happen. So that bending will be sensed by this the GB transfer function. It's like a sensor only. That sensor will sense that bending effect, so that bending effect will be given its output to that roll rate gyro also. Like whenever it is banking, so that the fuselage rate gyro also will be automatically compensated, so that the total aircraft will be banked like that. So if it is banked like that, in between any extra forces are acting on that. Any extra forces acting on that beam, no? So that forces will be sensed by that GB sensor. So that sensor will give it output to that roll rate gyro of fuselage also. So that forces will be avoided, and the bending will be avoided on the bending will be avoided on that aircraft wing. So the transfer function is a path corresponding to general low pass bending effect with resonance occurring at the bending modes of the wing. So because of the wing bending modes are relatively low in frequency, so they may contribute significant phase shift and possibly gain changes within the bandwidth of roll rate loop. So the bending mode filter is designed to compensate these phase and gain changes. Like whenever these bending mode frequencies, like because of the transfer function, again the frequency response will happen. So due to that bending modes, that mode shapes, that frequency is very low. If it is generally it is very low because of that loads. Because anyway that way wing can withstand that load, so that it can compensate that loads, and that frequency response of that wing also very low. So that possible gain changes and bandwidth roll rate things also will be compensated by this sensor operation only. So that effect of this effect causes that undesirable variations in aircraft roll performance that result in the pilot flying aircraft less precisely. So the closed loop control of the roll rate is used to reduce the variation of roll performance with the flight condition. And if the feedback is changed as a function of angle of attack, the amount of variation in closed loop properties can be made relatively small. Like when this inaccurate flight conditions are happen due to this bending mode frequencies and abnormal frequency responses of this aircraft. So this should be avoided for a better control of the aircraft. So for that, closed loop control things have been installed and as well, so that closed loop control of the roll rate will be used to reduce this variation of roll performance. Okay, so while that roll time is constant feature of a linear smart perturbation model and gives no indication of maximum roll rate or time to roll through a large angle, it is relevant to that initial speed of response and control of smaller amplitude motion. So like when the roll time is a constant, and that linear small perturbation model gives there is no indication for maximum roll rate or time taken to make that roll rate for a large angle. So it is relevant to that initial speed of response control and the smaller amplitude motions only it will attain, so that error in that signal will be avoided. So here you see the figure 2. So here the variation between that roll time to the angle of attack. So for a F-16 model, for a higher angle of attack. You see here, when angle of attack is changes from 2 to 16, that roll rate is been that reciprocal time constant, that roll rate time constant have been gradually decreasing. So that the roll time is decreasing means what? When it is the angle of attack is increasing, the roll time will be decreasing only, because when it is a constant angle of attack, then only that higher roll rate we will generally attack. But when that angle of attack is increasing, that time that roll rate generally it will be down. I mean, it should be down. Then only that aircraft will be in stable condition. Otherwise, if it is both the times, if both the things are happening, so that it will be comes on unstable condition only. See, that plot is derived for by trimming that F-16 model in a straight level flight at a sea level with a nominal CG position over a range of speeds. The angle of attack is greater than 20 degrees. The roll pole coupled with spiral pole to that form a complex pair. So the landing approach takes place at a relatively high angle of attack. So the roll rate feedback may be needed to ensure good roll response. So also that satisfactory damping of the Dutch roll mode is particularly important during the landing approach and gusty crosswind conditions also. So our this F-16 model not equipped with flaps and landing gear. So the design of that augmentation loops will simplify the illustrated on low speed and low flight conditions. So, like here you see, whenever it is approaching to landing, so automatically that angle of attack will be higher only. So at that higher angle of attack, the damping Dutch roll mode is particularly important during that landing approach. Even when landing, that gust winds also will be getting its significance. So due to that gust winds also, aircraft need to be unstable. Otherwise, it will lose its stability, so that we can't control that. We can't attain that proper landing. So here the F-16 model is not equipped with flaps and landing gear, so that the design of augmentation loop will be simply illustrated for low speed condition only. So here the condition is for low speed condition only. So the landing approach takes place at a relatively high angle of attack, and the roll rate feedback will be needed ensure good roll response. Also, that satisfactory damping of Dutch roll mode is particularly important during the landing approach and gusty winds and crosswind conditions only. So our F-16 model is not equipped with this landing gear. So if we take the dynamics at zero altitude with the nominal CG position at take an airspeed at 205 feet per second. There the angle of attack is 18.8 degrees. The roll rate, the roll pole and roll pole rate is really quite slow. That is about 1.44 seconds only. And the Dutch roll is very lightly damped. That means that the damping ratio here you see the damping ratio is just 0.2 only. So that the conditions for the conditions attaining at roll rate, lateral direction, lateral equation of motion values will be like the beta, that slide slip angle, the rolling angle and rolling angle, pitch rate and roll rate angles, and elevator aileron deflection and the rudder deflection, and that constant values also. Here you see the set of values have been given like a matrix values only. So these matrix values will you know that these values have been, again we took it from that solution of that equation of motion only. So that null matrix, like A matrix, shows the state that not coupled back to any other state, and it can be omitted from state equation when the designing augmentation system. That the C matrix has been used to convert that output quantities quantities to degrees only. Like here the C matrix will be ultimately our goal is what? We need to give that angular input to that control surface only. How much degrees of that control surface is being moved, so that output signal will be in degrees only. So for that the transfer functions for different transfer functions for different rates will be like p by delta a. That transfer function is this one, and this is having minus 5.911 into s minus 0.5092 into s plus 0.2370 plus or minus j into j into 1.072 by s plus 0.0767 and to s plus 0.69 and to s plus 0.4027 plus j 2.012. Like this transfer function again, where we get, if you see that last class, how this transfer function from that differential equation we got, and previous that stability augmentation system part 1 lecture also, how this transfer function we got it for a rudder transfer function. This is rudder rate transfer function and the roll rate transfer function also. That Dutch, and here you see that different. When we are giving the control surface input, that how the deflection and what are the sign convention for that deflections also we have see here. When elevator is there, the trailing edge is down. The trailing edge is down means that elevator is operated like this. So you see here. So whenever this is an aircraft airfall section, and this is the elevator. So if it is in a downward direction, so that elevator is trailing edge is down, then that sign will be positive and negative pitching moment will take place. So when it is down, so that negative pitching moment, that means that pitching moment will be negatively will happen. When the when it is up, like if it is in upward direction, then the positive pitching moment will get. That means the positive pitching moment will get. That means when elevator is down, that will attain the pitching. When elevator is down, it will approach to landing. So in a simple way, if you remember. And for rudder, so if the rudder is there, so suppose so this is the rudder condition. So if rudder deflection is, the trailing edge is left direction. So suppose this is the rudder and this is the trailing edge. So if it is in left direction, so this is the left direction and this is the right direction. So when it is in left direction, this will be positive and the negative yawing moment. So this is a positive yawing moment and this is a negative. This is a negative yawing moment and this is a positive yawing moment. So when it is in left direction, so it will be like a negative yawing moment only. And for ailerons, so ailerons will be like what? So see here. So if ailerons are like this, so here the ailerons will be placed. So when the ailerons, the right wing trailing edge is down. The right wing trailing edge will be this one and the left wing. It is going forward. So this will be the right wing and this will be the left wing. If it is in downward direction. So if it is downward and if it is upward, like you see. So here it will be the right wing will be the right wing will be downward and the left wing will be upward. So if right wing is downward and left wing is upward, so due to that a negative rolling moment. So that means here it will, if it is if it is a downward, so downward means what this if this is the right wing and this is the left wing, the right wing is down. So right wing is down means suddenly it will bank like that. So due to that banking, what will happen? Sorry, here the banking will be negative. So here it will be so, so this one. Here it will be downward and here it will be upward. So suddenly it is downward means it will be rolled like this. So it will be rolled like this. So when the aircraft is like that, when this one will be downward and this one will be upward, so suddenly it will be turn like that. I mean, it will bank like that. So when it is bank like that, it will be negative one. When it is when left wing is upward and right wing is downward, then it will be bank like this. So when it is bank like this, and this one will be the positive rolling moment. So here the sign convention for positive and negative, why we are saying like this, because without this one, we can't give the control surface to move in which direction, or I mean, our requirement is which direction, we don't know. So for that case only, what is the negative moment and what is the positive moment? Because in the pilot display is there, no? In the display, if it is a negative moment or positive moment, he should know. When while we are while that flight is going on, which is positive moment, which is negative moment, like right direction, left direction, we can't define at that time. So for that, what is the default condition? So this means when it is a right side is there, then that is a positive, and left side is there, that is a negative. And right side your movement will be positive, and left side your movement will be negative. And right side pitching up will be positive, and pitching down will be negative. So if you make like that, if you make it a constant notation like that, then only you can know how that aircraft is being moving forward, how that aircraft is being getting the angle, and how that aircraft is being getting the direction. So for that case only, whatever the general notations we will follow for the control surface only, we have given here. So okay, so so the natural force will not be cancelled out of the P by delta A transfer function by the constant zero. So therefore, the coupling exists between the rolling and yawing motions only, and the Dutch roll mode and will not involve in some rolling motion. So therefore, the transfer function validates for MA state, moment in moment out state equation for multi-input, multi-output state equation for analysis. At lower angle of attack, natural force will be typically cancelled out of P by delta A transfer function, leaving only the roll substance and the spiral also. Like here, the Dutch roll and the Dutch roll and yawing motion, yawing motion will be coupled, like the coupling of rolling and yawing motion. If it is that your rolling and yawing motion is coupled, so that the together motion we will get it when we are applying the control factor. So then we are giving the if you are giving that input also, that at a lower angle of attack, the natural force may be typically cancelled, right? That natural, when we are at a higher angle of attack and lower angle of attack, just you see, no, that roll rates have been suddenly decreasing and suddenly increasing. So that will be cancelled out, and the whatever the required transfer function, that only will be activated, so that subsequent control input will be given to that circuit. So that two roll rate transfer function given above contains MMT zeros close to that origin. So this is because that the gravity will cause the aircraft to begin slides at the rolls. So if the dihedral is derivative, that means the C is negative. The aircraft will have a tendency to roll at the opposite direction, because the dihedral is the negative means what? So this is a positive condition. If it is like that, so this will be like a positive condition, and if it is like that, and so if it is a negative one, so the roll rate will be negative roll rate only will get. So this effect will be more pronounced in a slow roll rate when slide shift has a chances to build up. So that rudder to roll rate transfer function has another MMT zero, so that MMT zero value. So further away from origin corresponds to faster acting non-minimum phase effects only. So that the positive deflection of rudder directly produces a positive rolling moment, and a negative yawing movement. Like you see in the table movement and the table 1, a positive deflection on rudder movement. Positive means what? So when it is in left direction, that will be negative, and right direction, it will be positive. So when the positive rudder movement produces a positive rolling moment and a negative yawing moment. So because when it is in a negative direction, it will be in a positive condition. When it is in a positive direction, it will be in a negative condition. So same as for the rolling movement also, that positive rolling movement only you will take. The negative yawing movement rapidly leads to positive slightly. Like that yawing movement is negative, then that positive slides like it has to be positively go. Like that means right side has to go. That means what the roll rate will be positive. Positively it will happen, and then that the radar movement will be negatively it will happen. That means negatively means what? So this side it should happen. Left side only. That left side. This is the radar. So that radar movement will be left side. It should happen. So when it is left side, that means the negative yawing movement and positive rolling movement. So then only it will be going that positive direction. So same as vice versa. That left side if you need to go, when the rolling moment will be negative and yawing moment will be positive, so that positive yawing moment will be positive yawing moment is just you see that left side and top. The positive means right side turn and negative means left side turn. And the rolling moment also right side if it is rolled means positive, and left side if it is rolled means negative. So if you make it like that, if you remember like that, then only you can understand what is positive and what is negative. So that effect tends to cancel the initial positive role, and the MNP zero transfer function manufactures of that complete effect. So here you see that whenever we are getting that positive or negative moment with respect to this SAS system, why we are using that SAS system for here? Because when we are getting the positive moment or negative moment, that Dutch rail and the roll Dutch roll moment poles should be avoided, because of that one. That if it is going like that, and it may having a Dutch roll moment, so that Dutch roll moment should be avoided, and pure yawing moment should be required. So for that pure yawing movement and the avoidance of natural movement only, this lateral SAS system has been installed in this one. For that, what we need to do, that integrated, instantaneous roll rate, that radar feedback and the ground feedback also required. So that is what the GA, GF and bending filter feedback, and that noise filter feedbacks also required. So that is also been installed here. So this is all about this directional control system, directional stability augmentation system. So hope you understand with these two parts. Like part one will discuss on pitch rate, pitching augmentation system, and part two discuss about that directional augmentation system. So in the next class we will discuss on that control system augmentation, and that control system augmentation, and that significance, that importance of the significance with some examples also, like for pitch rate, pitch feedback, and what is the importance of this pitch feedback and roll feedback things also we will discuss on next class. So that's all about this one. So you can take your reference from these two textbooks. So if you have any doubts also, you can comment below, and you can refer these textbooks for your further clarification. So that's all about this one. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.